Okay, hello. My name is Jonathan Angelis. Today, for our first critical assignment preparation, we have been instructed to talk about the cellular respiration, the breakdown of glucose and palmitic acid, or also known as palmitate, and to see how much ATP those two can create. After that, we'll talk about maybe the changes those two pathways can go through if maybe the intensity level of the person's activity level goes up or goes down, or maybe the duration goes up or down. After that, we'll talk about limitations that they have that might slow them down, and a little summary of how we can kind of relate this to the real world. So if we get right into it, let's start off with our breakdown of glucose, our one molecule of glucose. It's going to be a 6-carbon chain molecule, and our first step is to break it down. So we'll break it down into 2 pyruvates through glycolysis. Right there. So already you can see that we already have some ATP made. So to create or to make glycolysis happen, we need 2 ATPs. But the needing or using it and creating happens. So we create 4 ATPs, but use 2. Meaning our net ATP is going to be 2. So the glucose, after glycolysis, turns into 2 pyruvates. This is just going to be 3 carbon chain molecules, and these molecules are just the previous step to what we really want. So through pyruvate oxidation, we will make acetyl-CoA, which is going to be a prime catalyst for our next step, which is the citric acid cycle, or also known as the Krebs cycle. But in that step of the pyruvate oxidation, we have our NAD plus oxidized to NADH. And it's important to keep track of those. So our acetyl-CoA goes into our Krebs cycle. Acetyl-CoA is combined with oxaloacetate and making citrate, citric acid cycle, or the Krebs cycle. And in this cycle, we create more NADH, which is 1, 2, and 3. We also create some ATP and some FADH2. And like I said, we'll keep track of all those molecules right here. So, here's my just describing the picture. Next we have, just on the left here, we have our pyruvate oxidation, keeping track of the NADHs too. So as you can see, it says 2, not just 1, because we have 2 pyruvates. So since we have 2 pyruvates, we'll essentially have 2 acetyl-CoAs, which means 2 rounds of our Krebs cycle. And let's take a look at our total molecule count on this next slide. So from our one round of the Krebs cycle, we have 3 NADHs, like we had said, 1, 2, and 3. We have 1 ATP made right here. And then we have 1 FADH2 made right here. But since I said we have 2 rounds of it, because we have 2 pyruvates, 2 acetyl-CoAs, we'll just multiply those molecules by 2. So our 3 NADHs turns into 6, ATPs turns into 2, and then FADH2 turns into 2 as well. And note that I have here plus 2 NADHs from pyruvate oxidation. So that's this right here. 1 pyruvate oxidation NADH, and then the second one, which I did not illustrate, it would be right here, just a whole another copy. So then that gives us 8 NADHs total, 2 ATP, 2 FDH2. Now, to get more ATP, we need to put the FADH2 and NADH into the electron transport chain. So for every NADH, we can yield 3 ATP, and for every FADH2, we can get 2 ATPs. So now if we just go 8 times 3, for ATP we have 24, 2 times 2, 4 ATP, 2 ATPs from the original Krebs cycle right here, and then 2 ATPs, let's not forget, that we got from our glycolysis. So our total would be 24, 28, 30, 32 ATP would be our net total ATP from glucose. Let's move on to our palmitic acid. That's going to be through beta oxidation. So our first step is to try to get that big 16 carbon chain molecule into 2 carbon molecules. Those 2 carbon molecules will be called acyl fragments, and that's going to be in this beta oxidation area right here. So as we are trying to break down that molecule into 2 carbon molecules, the acyl fragments, we'll also be creating our NADHs and our FADH2s just from just regular processes of creating the acyl fragments. So we're oxidizing the FADH and the NAD plus and FAD, I'm sorry. So once that's kind of broken down, we have our acyl fragments. Those acyl fragments will combine with the coenzyme A to create the acetyl-CoA, just like we had in our glucose. So this is our special molecule that we're trying to attain. So as you can see right here as well. So once we have our acetyl-CoA, we just do the whole Krebs cycle as well. We will yield ATP, we will yield more NADH+, more FADH2s, and we'll go through the electron transport chain again. So after all is done, the 16 carbon chain molecule will produce 129 ATPs, and as well as the breakdown of glycerol. The breakdown of glycerol will create 19 ATPs, giving us a total of 148 ATPs. This is my citing of the illustrations there. So for the changes of intensity, I kind of broke it up into 2 categories here, which is anaerobic and aerobic. So our first one is anaerobic, which is not needed. Oxygen is not needed for this category. The energy happens and occurs in the cytosol of a cell and produces ATP very quickly, but not for long. So this is kind of a situation where if you need to have lots of energy really quickly, like a burst of energy, something happened, you need to go to it very quickly, maybe like a car crash and you're trying to swerve out the way, or just maybe a fight or flight kind of incident. The burst of energy will last for about 30 seconds to about 3 minutes maximum. The other way is aerobic, and this will definitely requires oxygen because it's a longer duration. This will happen in the mitochondria of the cell. ATP production is slower, but it lasts longer because it uses fat, and then our bodies have plenty of adipose tissue to use. It's important to note that these pathways all work together at the same time. It doesn't matter. It's not one or the other. So, for instance, if right now I'm using more of the aerobic state because I'm not doing any high intensity, but that doesn't mean that I'm not using my anaerobic state as well. Some limitations. Right here is my first one: the low carb diet by itself, or maybe with the high intensity training. If these two combined or together or by themselves, kind of makes glycerol become the main pyruvate and NADH provider, and that makes it hard on the Krebs cycle to keep turning. Our next one would be the lactate forming by pyruvate and oxygen or hydrogen combining, because we can't get enough oxygen to our bodies when we're performing high intensity training. Obviously we know lactate can lactate turns into lactic acid in the muscle, which creates fatigue and cramping. When it comes down to the real world, like I said, everyday life requires these oxygen or requires these ATP pathways. The body is very efficient, so it likes to use maybe everything it can. So it won't just choose one way or the other. Every situation would be different. You need a quick response or doing something like I am right now, which is just talking and relaxed. I'm not expending a lot of energy. So that has been my presentation. Thank you very much.